For decades, we've been searching for a trace of the first objects that lit up the absolute blackness of the early universe. Now, thanks to the power of the James Webb Telescope, we are likely looking straight at the pioneers of the cosmos, at stars that were born from pure, primordial hydrogen-helium gas. At first glance, this that you see right now might look like an ordinary, distant galaxy. This is an image of light from just 400 million years after the Big Bang. And the galaxy you're looking at has been named Hebe. Everything suggests that it is filled with the legendary population 3 stars. These are the first stars that ever appeared in the cosmos and prepared the universe for our existence, even though they vanished in the blink of an eye. The Hebe galaxy, which Roberto Maialino's team from the University of Cambridge spotted in the James Webb Telescope data, is a relic from a time when the universe was only 3% of its current age. It was an extreme time. Hebe doesn't look like the Milky Way. It is compact, incredibly bright, and emits a glow when the universe was only 3% of its current age. It was an extreme time. Hebe doesn't look like the Milky Way. It is compact, incredibly bright, and emits a glow. Let's clarify the concept of population 3 stars, because they are the main protagonists here. In astronomy, we have a specific naming system that, well, goes backward in a way. We live in the era of population 1. These are stars rich in metals, meaning everything heavier than helium. Population 2 stars are older and poorer in these additives, but population 3 is the mythical beginning. These are the first stars that formed from pristine hydrogen and helium, right after the universe cooled down after the Big Bang. They didn't contain a single gram of carbon, oxygen, or iron. Those elements simply didn't exist yet. They had yet to be created, to be, in a sense, cooked inside the cores of these first stars. And these population 3 stars were absolute heavyweight monsters, no matter how you look at it. Extremely different from our calm sun. They were massive. We're talking about masses ranging from a dozen to even hundreds of times greater than the mass of the sun. Their temperature was so high that they shone with a blinding blue-white light, reaching tens of thousands of degrees more than our star. How do we know this? Since we haven't seen them, well, we can still figure out what they look like, because we know how matter behaves when you keep adding more and more of it. It becomes denser and denser, increasingly processing hydrogen and light elements like helium in its interior. Because of their gigantic mass, they also lived very fast and very intensely. Instead of burning fuel for billions of years, they used it up in just a few million, ending their lives in colossal supernova explosions. Greater pressure, more mass to process. It all happened much faster. It was these explosions that scattered the first heavy elements throughout the universe, from which planets and we ourselves were formed billions of years later. We are children of the stars. To understand why these first stars are so important, we must look at a process called stellar nucleosynthesis. This is a mechanism in which a star acts like a giant natural thermonuclear reactor. Under the immense pressure and extreme temperatures found in the core, lighter atoms like hydrogen collide with one another, fusing into heavier ones like helium, and releasing a massive dose of energy in the process. When the hydrogen fuel runs out, the star begins to compress helium to create carbon, then oxygen, and so on, and so forth, all the way up to iron. Population 3 stars were the first factories of these building materials. Without them, the universe would simply be a boring, empty space, filled only with two gases, hydrogen and helium. It was population 3 stars that introduced chemistry to the physics of the cosmos, turning a simple universe into a place where life could finally exist. But how can we be sure that these primordial stars are actually sitting inside Hebe? This is where spectroscopy takes center stage, one of the most powerful research methods in an astronomer's arsenal. Light is not just a wave, but also a carrier of information, a unique cosmic barcode. When we pass starlight through a prism or a diffraction grating, it splits into a spectrum. Every chemical element absorbs or emits light at very specific, unique frequencies. If we see dark or bright lines in specific places, we know exactly what is in the object under study, even if it's 13 billion light-years away. It's a bit like investigating the chemical composition of a distant campfire, just by analyzing the color of the smoke coming out of it. In the case of Hebe, scientists were looking for something that isn't there. And that is the most exciting part. The spectrum of this galaxy shows an absence of any lines characteristic of heavy elements. There's no trace of carbon or oxygen. Instead, the James Webb Telescope recorded something very rare, the signature of ionized helium. Ionization is a situation where an atom receives such a large dose of energy, say, some photons, that it loses its electrons. If we provide enough energy, for example, in the form of extremely strong ultraviolet radiation, we will rip those electrons from their orbits. Ionizing helium requires unimaginable energy, far greater than what is produced by an ordinary, mature star. Presence of ionized helium lines in the Hebe galaxy means that there must have been light sources with temperatures so high that they only fit one possibility: population 3 stars. Initially, in 2024, Roberto Maialino and his team had some doubts. They saw the helium line, but they weren't sure if it was a measurement error, or if the light came from another, closer galaxy that happened to be in the same line of sight. They needed proof, confirmation of identity, and that confirmation arrived with the detection of a second line, this time of ionized hydrogen, which came from exactly the same location as the helium. Hanna Ubler from Ludwig Maximilian University in Munich spent long hours analyzing this data to rule out every other possibility. When both peaks overlap, it became clear. We are looking at pure, primordial gas heated by the first generation of stars. Of course, in science, we rarely have 100% certainty on the first attempt. Daniel Whalen from the University of Portsmouth notes that although the results are incredibly convincing, the precision is still lacking to completely rule out the presence of trace amounts of heavier elements. If they were found there, well, Hebe might turn out to be home to slightly more modern, population 2 stars. However, at this moment, the population 3 model is the only one that consistently explains what the James Webb Telescope is seeing. But there is one more problem that keeps astrophysicists up at night. It's about the mass and density of these stars. Previous computer simulations suggested that the first stars formed mostly in isolation, in small, sparse clusters. Meanwhile, Hebe seems to be filled with them to the brim, suggesting that the early universe was much more dynamic and productive than we thought. Maialino's team, based on observations, calculated that most of the stars in this galaxy have a mass between 10 and 100 times that of the Sun. And this changes our understanding of how quickly galaxies could grow and evolve in such a short time after the Big Bang. We are entering a new era of astronomy, where the theoretical dark ages, cosmic dark ages, are no longer a mystery to us. Thanks to instruments like the James Webb Telescope, we are moving beyond just guessing what the beginnings of light looked like, or simply relying on calculations. We are beginning to see it with our own eyes, and what we've discovered in Hebe is really just the beginning of the journey toward a full understanding of our own genesis, written in atoms, forged billions of years ago, in the hearts of these blue giants.